Good day all and welcome to my channel. This time we are going to be looking at questions that WAEC possibly bring out over the years in chemistry. And these questions will be of help to those that are preparing to writing WAEC examination 2023 and other subsequent years. And it is the hope that it will help students a lot for those that will actually follow up the series as I run through. So you just stay tuned, and as I run through the series, just pick your pen and your book and then learn alongside. Now on the board we are having 8 questions. In this series we are going to be having 20 questions, but I will treat on the first 8 questions. Then after I'm done with the first 8, then I will introduce the other questions. So these questions are going to be coming from different topics in the world of chemistry, and it will be of help to students that are actually preparing for this forthcoming WAEC examination. Whether you are talking about the objective or the theory, just learn as I run through the series. Question 1. The byproduct of fermentation of sugar is, the byproduct meaning the minor product of fermentation of sugar is, of course we ought to know what sugar is. Sugar can come in the form of monosaccharide, can come in the form of disaccharide, and can also come in the form of polysaccharide. All right. So the fermentation of sugar is usually to the polysaccharide and to the disaccharide. Yes, meaning we can ferment polysaccharide and we can also ferment disaccharide. Now, what is fermentation? It's simply a slow microbial decomposition of a large giant organic molecule to releasing ethanol and CO2. Ethanol is actually the ultimate product that is obtained from fermentation, which is considered as the main product. Then while the byproduct or the minor product is carbon dioxide. We can ferment a polysaccharide known as starch. When starch is fermented, it is catalyzed by a series of enzymes. It is broken down by a series of enzymes, and then it ends up producing ethanol and with the release of carbon dioxide. But these are the steps. Firstly, starch is a polysaccharide, so it ought to be broken down to releasing a disaccharide. And of course, starch being broken down releases maltose, and maltose is a disaccharide. When maltose is in turn broken down, it releases glucose. Then when glucose is in turn broken down, it releases ethanol and CO2, which is carbon dioxide. Now you see these steps of breaking down processes. They are actually catalyzed by a series of enzymes. The enzyme that catalyzes the breakdown of starch to maltose is known as diastase. And diastase is obtained from a material known as malt. All right, so maltose is in turn broken down to glucose by an enzyme called maltase. Maltase is simply an enzyme that is obtained from yeast. Then while glucose is in turn broken down to releasing ethanol and CO2 by another enzyme produced by yeast known as zymase. And this zymase is also a very important enzyme. In fact, the most important step of fermentation process is this step that releases the ultimate product, ethanol, with the release of that CO2 as the byproduct. CO2 is carbon dioxide, don't forget that. Then this is a polysaccharide. That's the fermentation of a polysaccharide. We can also ferment a disaccharide. So it's not only to polysaccharides that you can ferment. We can ferment disaccharides. Now, disaccharides can be fermented, such as we have sucrose. Sucrose. Now, sucrose is a disaccharide that, when broken down by an enzyme called invertase, which is obtained from yeast, so it is yeast that produces this same enzyme. So yeast is a very important microorganism that is involved in fermentation process, or that is needed for fermentation. So it breaks down this to releasing glucose and fructose. But of course, you know that glucose is our ultimate product that we would want to work with. So glucose in turn will be broken down to releasing ethanol and CO2. So that enzyme that breaks down glucose to releasing this is still zymase, which is also obtained from yeast. So it means that the minor product that is obtained from fermentation, or the byproduct that is obtained from fermentation of sugar is carbon dioxide, which is option A. Then the next question, question 2, which of the following sugars is a product of condensation of monosaccharides? Which of the following sugars is a product of the condensation of monosaccharides? So when you condense monosaccharides, you can either obtain disaccharides or polysaccharides. By condensation, it means the elimination of a molecule of water. So it's just like you having monosaccharides plus monosaccharide. Now, of course, you know it gives a disaccharide. And how does it give a disaccharide? By simply the elimination of a molecule of water. So you can think of two monosaccharides. For example, when glucose reacts with glucose or condenses with glucose, it releases a maltose unit. You get the point? So it means by condensation, you need to eliminate a molecule of water from glucose in order to obtain maltose. You know, glucose has a formula C6H12O6. You can visit my video lesson on nutrition in biology, then you understand this better. C6H12O6 again. So by the elimination of a molecule of water, it means you are going to be having C12, then H22O11. So that is that about that. So of course, we are only interested in either a disaccharide or a polysaccharide, because it's only a disaccharide or a polysaccharide that can be obtained by the condensation of monosaccharides. All right, so let's check. The options that we are provided with, we have galactose, we have maltose, we have glucose, and we have fructose. Let's remove those monosaccharides away, because monosaccharides cannot be obtained from the condensation of monosaccharides. I don't know that you are getting it. So the thing is, it's very, very clear that you can't condense monosaccharide to form monosaccharides. It's impossible. So you only condense monosaccharides to form either disaccharides or polysaccharides. So looking at galactose, galactose is a monosaccharide, which is very wrong. Glucose is a monosaccharide, very wrong. Fructose is also a monosaccharide. The only disaccharide here is maltose. So like I said, it could be a disaccharide or a polysaccharide that can be as a product obtained from the condensation of monosaccharides. So the answer is B, which is maltose, a disaccharide. Then let's see question 3. Question 3. The cleansing effect of soap is low in acidic water because of Now I'm going to explain this in details. Soap is simply an agent that is used in bringing about cleansing action of probably washing and all that. Soap is advantageous and disadvantageous in some aspects. Now, what are the disadvantages of working with soap? We have soap, we have detergent. In the world of organic chemistry, we have what is known as soapless soap and soapy soap. Soapy soap is simply soap for short. The while soapless soap is regarded as detergent, which is also known as ABS, which is alkyl benzene sulfonate. That's another name for detergent. So looking at soap, the advantages of working with soap over detergent as well as disadvantages. I'll major on the disadvantages. Looking at the disadvantages of working with soap, one of the disadvantages of working with soap is that it forms scum in hard water. And the name of the scum that is formed when soap is used in hard water is known as calcium stearate or calcium octadecanoate. Calcium stearate or calcium octadecanoate. It will be calcium or magnesium, you get. So you could replace the calcium with magnesium. It's the same thing. So you cannot use soap in hard water. Why? Because of the fact that it forms scum, and this scum tends to make our fabrics that we are washing to have these scars on them. So that's why it's disadvantageous. Another disadvantage of working with soap is that soap cannot be used in acidic water. Remember what an acid is? According to Svante Arrhenius, he said acids are substances when dissolved in water produces hydrogen ion as the only positive ion. So it means In acidic water, there must be excess of what? Hydrogen ions. And this excess of hydrogen ions that are present in the water would interact with the soap. And when soap tends to interact with excess of these hydrogen ions, it tends to result in the formation of unionized fatty acids. So that's the reason why it will not decrease the cleansing effect of the soap. So the answer to this question is that the cleansing effect of soap is low in acidic water because of the formation of unionized fatty acids. All right. So that's for number 3. Then number 4. Number 4. The following compounds are condensation polymers except the following compounds are condensation polymers except. Now this is taking our minds to our polymerization concept, talking about polymerization as a concept in organic chemistry. Now looking at the word polymer, polymer is simply a large molecule that is obtained from the simple combination of small molecules known as monomers. So when you combine monomers together, monomeric units together, it forms a large molecule called polymer. That process of combining these small molecules to form this large macromolecule polymer is called polymerization. So it is by polymerization that you obtain a polymer. And there are actually two types of polymerization. What are the two types of polymerization? We have the addition polymerization. We have addition polymerization and we have condensation polymerization. These are the two types of polymerization that we have. Addition polymerization and condensation polymerization. Now, considering the addition polymerization, when we talk about addition polymerization, what are we referring to? We are referring to a type of polymerization in which it involves the combination of two or more monomers, usually of identical forms. They are usually identical in nature, without the elimination of a small molecule. The combination of two or more monomers that are usually identical in nature without the elimination of any molecule, any small molecule. So this one, what are the key things to consider about addition polymerization? One, they have identical monomers. That's one. And secondly, without the elimination, of small molecules, all right. So then it means that addition polymerization will be a direct contrast to condensation polymerization. So in the case of condensation polymerization, this one talks about, it could be that the monomers could be identical or they could not be identical. It all depends. Sometimes they might be identical or sometimes they might not be identical. So it could be they may or may not be identical monomers. That's for condensation. Then secondly, it involves the elimination of a small molecule. Elimination of a small molecule. That's for condensation polymerization. I'll make this thing to be clear, very lucid. Looking at condensation polymerization, that elimination of small molecules simply means that you are eliminating usually water molecule. Usually, in most cases of condensation polymerization, it is water molecule that is usually eliminated. Now, looking at this addition polymerization, classical examples of polymers that falls under the addition polymers includes, we have polyethene, we have polychloroethene. These are examples of addition polymers. Then we also have polyphenylethene. These are examples of addition polymers. Now, if you observe, the units that form these polymers, they are identical in that polyethene is actually obtained from monomers ethene. So how do you even identify the monomers of addition polymers? Very easy. Just simply remove the poly and then you are left with their monomeric unit. The monomer of this is ethene, the monomer of this is chloroethene, the monomer of this is phenylethene. Alright. Now chloroethene is also known as vinyl chloride. That's another name for it, vinyl chloride. So you can also refer to this as PVC, which is polyvinyl chloride. Alright. Then while this one, phenylethene, is also called styrene. So you can call this polystyrene, it's the same thing. So all these are classical examples of addition polymers. Then looking at condensation polymers, we have classical examples such as nylon 6,6. Yes. Then we also have other examples, terylene. We have terylene. Then we also have starch. Then we have protein. Yes. Now this starch and protein, they are natural polymers. That's natural condensation polymers. Then while terylene and nylon, they are synthetic or artificial or man-made polymers. All right. Now if we even look at nylon, there was something I said about condensation polymerization, that they may or may not be of identical monomers. Looking at nylon, the monomeric units that result in the formation of nylon 6,6 are not identical. So it means they are not the same. And what are the monomeric units? We have the hexane 1,6-dioic acid and hexane 1,6-diamine. So these are the two monomeric units that tend to condense with the elimination of a molecule of water to result in the formation of nylon 6,6. Looking at starch and looking at protein, yes, if you look at starch is a polysaccharide. So when you combine multiple units of monosaccharides such as C6H12O6 plus C6H12O6, if you have visited my video lesson on the biology class on nutrition, you can actually check below, you see it there, that I explained how you can obtain the general formula of polysaccharide, and starch being a polysaccharide can be controlled by that. So for you to form a glycosidic bond, there must be the elimination of water molecule. Hence, from here you are going to be having C6H10O5, and it's a continuous chain. So hence, at the end, you will obtain C6H10O5 as a continuously produced substance, all in N, where N represents a large number. All right. So it means that since you are eliminating water molecules subsequently, that is an example of a condensation polymer. Then looking at protein, it's the same thing too, because now for proteins, for you to obtain protein, you have to condense several units of amino acids. And I've been able to explain amino acids in one of my video lessons, that amino acid has a chiral carbon which is connected to 4 different groups. So we have NH2 amino group, carboxylic group. We have RO, the alkyl group, and H. So if you have, let's say, another amino acid, let's say NH2, then linked to carbon, and then just identical units here, and then COOH. If you want to form a bond here, there must be the elimination of a molecule of water, meaning OH will be removed from here, one H will be removed from here. Then you are now left with CONH. So this is called a peptide bond. Of course, peptide bond is an example of an amide. All right. So when you now form several units, let's just picture it this way, that we are having several aggregate units of these amino acids. We are going to be forming several peptide bonds. At the end, we will now obtain polypeptide bonds. All right. So that's that about that. So hence, from all my explanations I've just explained, it will be very, very lucid that we can be able to obtain our answer to this question. The following compounds are condensation polymers, except already this is condensation, this is condensation, this is condensation, while this one is addition. So the answer becomes D. All right. So that's our answer. Then question 5. Question 5. We are asked, what amount of electricity is required to deposit 1 mole of aluminium from a solution of aluminium chloride, AlCl3, from a solution of aluminum chloride AlCl3. Now this question is coming from the Faraday laws of electrolysis, talking about the Faraday's second law of electrolysis. Now looking at the Faraday's second law of electrolysis, it states that when the same quantity of electricity is passed through different electrolytes, the relative number of moles of the elements discharged is inversely proportional to the charge on the ions. And of course, let me break that big statement down. If I ionize this, or I dissolve this in a solution, it's going to certainly give me Al3 plus Cl minus. Yes, because this 3 is obvious it came from this one. Then while the Cl is just having its negative charge like that. So by the exchange of ionic radicals, they would end up forming these compound. You get? So that's it. Now, looking at that law, one mole of sodium ion, in terms of summary of explanation of that law, deposits 1 farad, meaning the charge here. Then 1 mole of calcium ion deposits how many farads? 2 farads. Then 1 mole of aluminium ion, in this case, because we now have the ionized form of aluminium, will deposit 3 farads. So it's very, very easy for you to spot out the answer. What amount of electricity is required to deposit 1 mole of aluminium from a solution of aluminium chloride? Of course, the answer becomes 3 farads or 3 Faradays. All right, so that's that about that. Then let's move on to the next question. Question 6. If 6 grams of N combines with 24 grams of oxygen, what would the empirical formula of the oxide be? This is taking our mind to empirical formula. All right, now we have M and then we have oxygen, so you bring them out. M and oxygen is an oxide though. So now we are given the gram of M to be 60 grams, so bring it out, 60 grams, and we are giving our oxygen to be 24. So our oxygen is 24 grams. The reason why we are provided with the relative atomic masses of each of the elements is for we to actually use it to work and get our correct answer to our empirical formula. So in this case, we are giving our M to be 120. So it's very easy for we to now divide by the relative atomic mass. That's what they usually do whenever you are carrying out your empirical formula determination. So you have to divide this by 120 and you divide this by the oxygen being 16. All right, so with the help of our calculator, we can easily get this. So 60 divided by 120, that gives us 0.5. So that's the first step you do. You divide first with the relative atomic mass. Then now the next is 24 divided by 16. So that gives us 1.5. So from here, you can easily tell what to do. Simply divide by the smallest value, which is obvious is 0.5. That's 0.5. So this into this is 1. Then 1.5 divided by 0.5 is obvious is 3. So 1.5 divided by 0.5, that's 3. So that becomes 3 here. So it's very easy that our empirical formula would now be M, which is just with one value. You don't need to write the 1 there. Then O3. So this becomes our answer. So the answer is C. All right. Then question 7. Determine the quantity of electricity used when a current of 0.2 amperes is passed through the electrolytic cell for 60 minutes. Now we are told to determine, this under electrolysis, the quantity of electricity. When we say quantity of electricity, Q, quantity of electricity is also known as the charge. Quantity of electricity is also known as the charge. All right, and remember that charge is measured in coulombs. Don't forget that, in coulombs. All right, so don't forget that Q is equal to current times time. So for you to obtain your charge or a quantity of electricity, you have to multiply the current provided by the time. But usually your current must be in amperes, then while your time must be in seconds. That's the standard unit of time. So in this case, we are given that we are told to determine the quantity of electricity, be Q now, which is Q here now, equal to, our symbol of current is I, then our symbol of time is T. All right. So we can easily plunge in our values. Now we are given the I is 0.20 amperes. So our I is 0.20 amperes. Then our time is 60 minutes. 60 minutes. So 60 minutes. Now, 60 minutes is not the standard unit of time, it's seconds. So what do? For you to convert minutes to seconds, you simply multiply by 60. When you are converting minutes to seconds, you multiply by 60. That's the shortest cut to it. Then when you are converting hours to seconds, you multiply by 3,600, meaning 60 times 60. So in this case, it is very, very easy for you to get your seconds. All you simply do is just say 60 times 60. That gives us 3,600 seconds. So it means we'll be working with this value. All right. So that becomes Q is equal to 0.20, which is our current, then times 3,600. And when we do that, it ends up giving us, I think, 720 times 3,600. So that becomes 720. So it's 720 coulombs. So our answer to this question is D. All right. Like I said, if you are converting from hours to seconds, it's very easy. Just multiply by 3,600. So it's just like you being asked the question, 2 hours, how many seconds are present in 2 hours? Very easy. Just 2 times 3,600, you get your answer. So let's continue. Question 8. Question 8. If 5.0 gram of marble reacts with 25.0 cm cube hydrochloric acid, which of the following combinations has the fastest reaction rate? A. Marble chips and 2.0 mol per dm cube HCl. B. Marble chips and 2.5 mol per dm cube HCl. C. Powdered marble and 2.5 mol per dm cube HCl. D. Powdered marble and 2.0 mol per dm cube HCl. This question is coming from the rate of chemical reactions. I've explained that in one of my video lessons on the rate of chemical reactions. You can actually watch the video below. All right, you can refer back and then check it. Now, looking at this, there was something I said about the rate of chemical reactions. What increases the rate of chemical reactions in terms of the surface area of the reactant? When the surface area of the reactant is very large, the reaction rate tends to be very fast. Yes, so the smaller the surface area, the lower the rate of reaction, or the slower the rate of reaction. Then the larger the surface area, the faster the rate of reaction. Yes, just like I explained even in the video, telling students that you are having wood and sawdust of equal masses, and of course you are burning both of them. The one that burns faster is actually the sawdust. Why? Because the sawdust has a larger surface area when compared to the wood. All right, so that's what is very, very important. You should take cognizance of from the options. Again, in terms of concentration of the reactant, when you have a higher concentration of the reactant, it tends to increase the reaction rate. And then when the concentration of the reactant is very low, it brings about a very slow reaction rate. So let's get it done now. Marble chips, the surface area here is small, so it means A and B are out of it. Why? Because both of them, they have small surface areas. Marble chips, marble chips. Then we are now left with between this and this, because this one will have a large surface area. So powdered marble with large surface area, same with this one. Now, which one, since this one has obeyed the principle of large surface area, then in terms of the concentration, let's confirm 2.5 mol per dm cube of ACl and 2.0 mol per dm cube of ACl. Which one has a higher concentration? It's obvious it's 2.5. So it means you can just dissect this question with smiles on your face, and then you get your answer. So powdered marble and 2.5 mol per dm cube. This one has a very large or big concentration. The concentration is high and the surface area here is large. So it means this will be with the fastest reaction rate. All right, so the answer is C. But let me ask this brain teaser question now. See from this, which one will have the slowest reaction rate? Of course, you know that you have to look for the one that has the lowest concentration, and again the one that does not have a large surface area. So let's confirm. Marble chips and 2.5. This one has a high concentration, but you're having a low surface area or small surface area, while this one is having a small surface area and a small concentration. So the answer is this one. That's the one that we have the slowest. Then the one that we have the fastest still remains this. All right. So you can visit the video lesson on rates of chemical reaction. Then you get to understand this better. Now to the next set of questions. Number 9, what number of moles of oxygen would exert a pressure of 10 atm at 320 Kelvin in an 8.2 dm cube cylinder? Now this question is taking our mind to ID gas equation, which is PV equal to nRT. Now, of course, you know P represents pressure, V represents volume, N represents number of moles, then YR is the gas constant, then T is temperature. So we can just plunge in our values directly and then we'll get the number of moles, but we are told to calculate number of moles being our N there. So our pressure is given to be 10 atm. So in place of pressure, we'll put 10 times our volume. Our volume is 8.2 dm cube, which is 8.2 equal to N times 0.082, which is our arrow, then times our temperature is already in Kelvin, so no need of conversion, 320. So when we do that, our N would now be equal to 10 times 8.2 divided, because we are dividing all through by these two values in order to make N stand on its own, 0.082 times 320. So with the help of our calculator, we are having 10 times 8.2, that's 82. Then this will be 82 over then 0.082 times 320, that becomes 26.24. So when we carry out the division, 82 divided by 26.24, that becomes 3.125. So 3.125, approximately 3.13, because 5 can approximate or round off. So that's our answer, 3.13. Option C is the correct answer. Then number 10, still on calculations. Number 10, if 50 cm cube of a saturated solution of potassium nitrate KNO3 at 40 degrees Celsius contained 5.05 grams of the salt, being the salt, its solubility at the same temperature would be, so we are told to calculate solubility. Now, for calculations involving solubility, the simplest approach or formula is given as 1000 m over mv. Always remember this. This is solubility in mole per dm cube. That's the formula, where this small letter m represents the mass of the solute, being the salt usually. Then this big letter m is the molar mass of the salt. All right, then while this one is the volume of the solvent, or the solution rather, the volume of the solution. So in this case, we are given the mass of the salt being 5.05. So it means our small m is 5.05 grams. Then we also given the molar mass. In fact, they've even calculated it for us. So the big letter m there is 101 per mole. That's our unit of molar mass. And then we're told to calculate, we're given the volume. What volume are we given? 50 cm cube. Very easy. So our volume is 50 cm cube. Then we are told to calculate the solubility in mole per dm cube. Very easy. Just plunge in your values there. That becomes 1000 times our small m. The small m is 5.05 over, then our molar mass is 101 times our volume is 50. So when you do that, it becomes 1000 times 5.05, that becomes 5050, 5050, then 101 times 50 is still same as 5050. So our answer ultimately will be 1. So we are now having our answer to be 1 mole per dm cube. So that's our answer. So the answer is A. Question 11. Which of the following elements would displace copper from a solution of copper ions? Now, this question is taking our mind to our activity series, proper understanding of the activity series, most especially the cations, because the proper understanding of cations, being the positively charged ions, will help you to attempting a question like this correctly. And most times students, they don't really remember the activity series, but you can use a code to always remembering it easily. I'm going to drop the code or a mnemonic that you can use to always remember your activity series, most especially the cations. And what is this mnemonic? It goes like this: please stop calling me a zebra. I truly like her calling me super powerful giraffe. I go all over that again. Please stop calling me a zebra. I truly like her calling me super powerful giraffe. Let me write it on the board. Please stop calling me a zebra. I truly like her calling me super powerful giraffe. Now let me tell you what each of them represents. You see this P here? The P represents potassium, then the S represents sodium, C represents calcium, then M represents magnesium, A represents aluminium, then Z represents zinc, I represents iron, then T represents tin, then L represents lead, then H represents hydrogen, then this other C represents copper, then M represents mercury, then S represents silver, then P represents platinum, then G represents gold. But some texts omit this platinum because they believe that gold is more reactive than platinum, because it's believed generally that electropositivity decreases down this lane. All right. Then the symbol of potassium is K, sodium is Na, calcium is Ca, magnesium Mg, aluminium Al, zinc Zn, iron Fe, tin Sn, lead Pb, then hydrogen we have H, then we have copper Cu, mercury Hg, silver Ag, then platinum Pt, and gold Au. All right, AU. So these are actually their symbols. So you can use that code to always remember. So looking at this question, we're told which of the following elements would displace copper from a solution of copper ions, meaning those ones that are higher up than copper can displace copper from a solution of copper ions. So if you check, we are having silver. Silver is lower. This is silver, lower. Then we have gold is very low. Then we have lead is higher than copper. In this case, this is lead. And then we have mercury is lower than copper. So in this case, we are having this and this lower, then the answer is lead. So lead can displace copper from a solution of copper ions. All right. So question 12: what is the percentage composition of carbon in this compound? The percentage composition of carbon in that compound. So let's go. Looking at the compound there, we are having CaHCO3 2. So we are told to calculate the percentage composition of carbon in this. Very, very, very easy. Now, how do you get it? Percentage composition of a given element is given by the relative atomic mass of the element, the relative atomic mass of the element, then over the relative molecular mass of the compound, molecular mass of the compound, then times 100%. All right, so that's how you get it. So it means that we have to get the relative molecular mass of this compound first. That's even the reason why we are giving their relative atomic masses of the elements. So for calcium is 40, so 40 plus, then let's get the sum up of everything here. Hydrogen is 1 plus 12 plus 16 times 3 being 48. So this is 48 plus 48. So it becomes 1 plus 12 being 13, then 13 plus 48. 13 plus 48 is 61. Then that 61, which is the whole of this, times 2, because 2 is affecting everything there. That becomes 61 times 2, that's 122. So that becomes 122. So when you sum up these two, it becomes 162. 162 gram per mole. So this is the relative molecular mass of the compound. Then in this compound, what is the relative atomic mass of carbon in this compound? Since we were told to calculate the percentage composition of carbon, we are only interested in carbon there, so which is the element in question. So now we know the relative molecular mass being this one. Then let's get the relative atomic mass of the element in the compound. Already carbon here is 12. Then 12 times this 2, that becomes what? 24. So we are getting the relative atomic mass of carbon in the compound. So the relative atomic mass of carbon in the compound becomes 12 times 2. That becomes 24 grams. So if that is our relative atomic mass, then it means that it will be very easy for you to get it from the percentage composition of carbon. That becomes 24 over 162 times 100. So what we'll do that with the help of our calculator, 24 divided by 162 then times 100, that gives us 14.8. 14.8. So the answer is B, 14.8%. All right, so that's how you calculate percentage composition questions. So the next question, question 13. Which of the following bond types is intermolecular? Of course, you know, in bonds we are having the intramolecular bonds, we have intramolecular bonds, and we have the intermolecular bonds. Intermolecular bonds, intramolecular bonds. Now, for intramolecular bonds, they are simply bonds that exist within molecules. That's the key word, within molecules. Then while for intermolecular bonds, they are bonds that exist between molecules. All right. So what are classical examples of these bonds under the intra? We have electrovalent bond. Electrovalent bond is also called ionic. That's another name for electrovalent bond, ionic bond. Then we also have covalent bond, and we have metallic bond. Now we have a special type of covalent bond which is called dative or coordinate covalent bond. It still falls under this. Then under the intermolecular bonds, we have hydrogen bond. Then we also have the van der Waals force. All right. So it's obvious that the only intermolecular bond amongst these series is actually hydrogen bond, because covalent is intra, ionic, which is also electrovalent, is intra, then metallic is also intra. All right. So the answer is B. Then question 14. We are told to give the IUPAC name of that organic compound. The full meaning of IUPAC is International Union of Pure and Applied Chemistry. All right, International Union of Pure and Applied Chemistry. So if we are told to give the name of this compound, let's represent based on structure. This is CH3, which is this one. Then the next is C, then H. Then because of this bracket implies that this compound is directly attached to this carbon coming before it. So it becomes CH3, which is attached to this carbon. Then let's continue. This one, C, then H, then linked to CHH. But since we're only having just two, we don't have anything on top of each of the carbons, it implies that there is another bond that is formed here. Because due to the presence of this bond, you can't be having anything written on top of each of these carbons. So that's the reason why we didn't write anything there. So it's obvious we've been able to represent the structure there. So what's the next step? We need to name it. This is a member of the alkenes, that's alkenes, because alkenes are generally known to be characterized by their carbon-to-carbon double bonds. So you give priority to the double bonds, meaning if you go by forward numbering, this is 1, 2, 3, 4, that's numbering the carbons forward. Then backward is 1, 2, 3, 4. Then look at the carbons that are linked by the double bonds. Going by forward is position 3 and 4. Then backward is position 1 and 2. So between 3 and 4 and 1 and 2, which one is smaller? It's obvious that is 1 and 2, because how do you get it? 1 plus 2 is what? 3. 3 plus 4 is what? 7. So 3 and 7, which one is smaller? It's obvious it's 3. So we are going with the backward, and you are sticking with a particular direction all the way. So since we are going with backward, you should go with it all through. So it means that between 1 and 2, which one is smaller? It's obvious it's 1, so you go with the 1. That's another rule. Then going by the backward, we have this compound being methyl. This is a methyl group. Is seated in what? Position 3. Don't go with the forward. Since we are going with the backward because of this functional group, giving priority to it, you have to stick with the backward. So the position where you can find that group is 3. So you write 3 methyl. That's where you can find the methyl group coming by backward numbering. How many carbons are you having in the parent chain? It's obvious it's what? 4. And that's what? Boot. So 4 carbons is to boot. So boot what? We went to 1. So it becomes 1, then what? In, being the functional group. Alright? So the answer to this question is 3 methyl boot 1 in. Don't worry, I'm going to treat an organic chemistry series very soon. And then I will expose everything about the world of organic chemistry 1 and 2 in the series. Alright? So just stay tuned to this channel. Then the next question, which is question 15. Question 15. If the molar mass of this compound XHCO32 is 162 gram per mole, determine the relative atomic mass of X. So we are giving this compound X, then HCO3, then 2. Then we are giving the molecular mass of the compound to be 162 gram per mole. All right. Then we are told to determine the molecular mass of X. Just like, let's picture it this way, like we are giving this kind of compound NaOH, and we are told to calculate the relative molecular mass of this compound. It's very easy. The relative atomic mass of sodium is 23, plus that of oxygen is 16, that of hydrogen is 1. When you sum up everything, it gives 40 gram per mole. I'm just giving you an illustration. Let's now picture it this way, that they now heat this element XOH, and then we are told that same thing, the relative molecular mass is 40 gram per mole. So we are told to calculate the relative atomic mass of this X, being sodium, but we have heat it here. So how do we get it? It's the same thing. All you simply do is just to sum up. It becomes X unknown plus oxygen remains 16, hydrogen is 1, equal to 40. And when you do that, it becomes X plus 17 equal to 40. So to get X, what do? You collect like terms, you move the plus 17 to the other side. That becomes X equal to 40 minus 17, and that gives us 23, which is this, our sodium. So it's still the same thing that we are going to do here. I just did this for you to understand what we are about looking at now. So in this case, this becomes X plus, we don't know X now, the whole of this. Let's get everything about this and then multiply by 2. H here is 1 plus carbon is 12 plus oxygen is 16 times 3 is 48. So all in what? 2. So that becomes equal to what? 162. That's our relative molecular mass of the whole of the stuff there. So X plus 1 plus 12 is 13. Then 13 plus 48. 13 plus 48. That gives us 61 times 2. That gives us 122. So this becomes 122 equal to 162. So to get x, it becomes x equal to 162 by collection of like terms. When this one crosses, this plus will turn minus and move with it. That becomes minus 122. So x equal to 162 minus 122 is obvious is 40. 162 minus 122, that's 40. So our x is 40. That's our relative atomic mass of x. So the answer is A. Then question 16. Question 16. Which of the following oxides is amphoteric? Now we have different kinds of oxides. We have the acid oxides, we have the basic oxides, we have the neutral oxides, we have the peroxides, we have the amphoteric oxides. But we are interested in the amphoteric oxides. Amphoteric oxides are simply oxides that possess both acidic and basic features or properties. So what are classical examples? I have treated this in one of my video lessons. We have acid oxides. This carbon 4 oxide, CO2, NO2, which is nitrogen 4 oxide, PbO, lead 2 oxide, CaO, calcium oxide. Now, oxides of non-metals usually are called acid oxides. So CO2 and NO2, both of them here, they are acid oxides. Acid oxides are also called acid anhydrides. Acid anhydrides. You can visit my video lessons on acid, basic, source, and water. Then you understand this better. Then calcium oxide. Calcium is a metal, so this is an oxide of a metal. So this is an example of a basic oxide. But those special metals that form oxides, which are known as amphoteric, they are unique metals. And classical examples include Pb, Sn, Zn, then Al, and Be. Now, these elements, unique metals, they have the tendency of forming amphoteric oxides. That's lead, tin, zinc, aluminium, and barium. They form amphoteric oxides. All right. So the answer to that question is C, which is lead oxide. Then question 17. Charcoal is used in the decolorization of sugar because of its. Charcoal is used in the decolorization of sugar because of its. Of course, you know that we have different kinds of charcoal. We have sugar charcoal. We have sugar charcoal. We have animal charcoal. Under my lesson on carbon and its compounds, you can visit that lesson and then you understand different types of amorphous forms of carbon, talking about charcoal as one of them. And then we now have different types of charcoal. Then we now have wood charcoal. Wood charcoal. In that lesson, I explained the uses of these charcoals. I told you that wood charcoal can be used in the adsorption of poisonous gases and also for the purification of noble gases. Animal charcoal is commonly employed in the adsorption of coloring matter, which is even very important in this kind of question now. So generally, charcoal rather, they are known to have this adsorption property, not absorption. The word absorb means to penetrate or go in, while the word absorb means to stay on the surface. So it is adsorb, not absorb. So the answer is D. So that's how animal charcoal works. Based on the principle of adsorption, it's able to remove coloring matter from substances. So that's our question 17. Question 18. A hydrogen chloride gas reacted with oxygen gas to yield water and chlorine gas. The mole ratio of the hydrogen chloride gas to water is, this is under balancing of reaction. Let's balance this reaction. A hydrogen chloride gas reacted, that's HCl gas, reacted with oxygen gas, O2 gas. Then we are told to yield water, H2O liquid, then plus chlorine gas, Cl2 gas. So let's balance the reaction. We are told that the mole ratio of hydrogen chloride gas to water is, so we are only interested in this and this, but let's balance first. How many hydrogens are we having here? 1. Over here is what? 2. So we have to make here 2. Then how many chlorines? 2 chlorines, and over here is 2. So it means we balance hydrogen and chlorine. But look at this. Oxygen over here is what? 2. But here is what? 1. So what do? We have to make here 2. So 2 oxygen, 2 oxygen. But then again, since we have introduced 2 here, we have also altered hydrogen. So in this case, our hydrogen now is 4, which is 2 times 2. But here is what 2. So we have to remove this 2 and make it 4. Then now we have also altered chlorine in this case. Chlorine here is 4, then here is 2. So we have to make here 2. So everything is balanced now. 4 hydrogen, 4 hydrogen, 4 chlorine, 4 chlorine, 2 oxygen, and 2 oxygen. Everything is balanced. But now the question, the mole ratio of hydrogen chloride gas, meaning HCl gas, to water, H2O, from the balance reaction, because we are only interested in these two. So I just drew them out now. And then this becomes, what's the mole ratio? The ratio is 4:2. And if you check the options, there's nothing like 4:2, meaning these two. There's nothing like that. So we only have 1:3, 2:1, 3:1, 4:1. But you know, in this kind of case, we can reduce this. We can reduce this by 2. 2 into itself is what? 1. 2 into 4 is 2. So this becomes 2:1. So the answer is B, 2:1. So that's how you attempt questions like that. Then question 19. Electropositivity of elements across the periodic table. Normally, you know, that's under the periodic properties of elements when talking about the trend of the periodic table. Now, we have periodic properties of elements, and what are they? We have electropositivity, we have electropositivity, we have electronegativity, we have atomic radius, we have ionic radius, we have electron affinity, and we have ionization energy. These are periodic properties of elements. But our main focus here is on electropositivity. Now, what is electropositivity? It is the ability of an element to lose electrons and become positively charged. And that feature is exclusive to metals. All right. And in terms of the trend, it's DAP and it's IDG, meaning it decreases across the period and it increases down the group. So the correct answer to this question is that it decreases across the period and it increases down the group. So the only one that is very correct here is C. So take cognizance of that. All right. Then looking at question 20, the electron configuration of carbon atom. The electron configuration of carbon atom in its excited state is, of course, this question is taking us to orbital configuration. When we talk about orbital configuration, there is actually an energy gradation system that is often employed. That is 1s, 2s, 2p, 3s, 3p, 3d, then 4s, 4p, 4d, and 4f. Just like that, it's a continuous stuff, all through to 7. Then taking it like this, going slant, then you'll be having the first to be 1s, coming down, 2s, then 2p, 3s, then 3p, 4s, and so on. All right. And s, you know, all these letters, they represent s, p, d, f, meaning the types of orbitals. That's the sharp orbital, principal, diffuse, and fundamental. S orbital takes only 2 maximum. This one takes 6 maximum. This one takes 10 maximum. This one takes 14 maximum. All right. So going by that configuration, normally carbon has how many electrons? Carbon has 6 electrons. So if we are filling the 6 electrons, it's going to be 1s2, 2s2, being that s takes maximum of 2 electrons. Same with this one, 2 electrons. Then move to the next, 2p2. This is the orbital configuration of carbon in its ground state or normal state. Ground state of carbon. But when you are talking about the excited state of carbon, you have to be extremely careful because the excited state of carbon is different from the ground state of carbon. Okay, let me go by image representation diagram. Now let's say we have something like this. Now remember that this is 1s, this 2s, and this 2p. By ground state, it becomes something like this, then like this. So in this case, we are having 1s2, 2s2, 2p2. This is ground state of carbon, ground state of carbon. Then for the excited state, what happens is that the proximal s to the one with the highest energy level tends to lose its electrons to the one with the highest energy level, and then one will leave here and leap to join this one. So in this case, this is the excited state, and the excited state is represented with 1s2, 2s1, and 2p3. Yes, because one has left this place, so we are left with only one electron, and that one electron that has left has joined the 2p. So in this case, you can now split this into the x, the y, and the z letters representation. That becomes 1s2, 2s1, 2px1, 2py1, and 2pz1. So that's how it is. So the correct answer to this question is option C. I'm still going to be having multiple classes on all this for you to better understand the concepts, treating them as topics. So we have come to the conclusion of this video, and it's my hope and prayer for every WAEC student to come out excellently well with their forthcoming exam. I wish you guys all the best. Don't forget to invite your friends to this channel. Stay tuned to this channel to get the very best, and subscribe to this channel. Don't forget to always hit the like button if you like this video, and also place your comments if you are confused about any point. I wish you guys all the best. Thanks for watching, and